Okay, so I'm not sure what I was in the middle of saying, but really important. Find an inverse, switch x and y, right? Okay. Now there is going to be new notation. Okay, so this is how we can notate. It goes along with function notation. Like we just call a function f of x. That's going to be like the original function. And then if you want to talk about its inverse, you write it like this. F with something that looks like a negative 1 exponent, and then of x. Okay. And to say that, I say f inverse of x. So I just read that negative 1 exponent as an inverse. You don't really say like f to the negative 1. That's not what it is. It's just a notation for the inverse. So it's saying it's not the original. It's the one where you switch x and y and then you solve for y. Okay. Of course, you can have like g inverse of x, or like if you're just working with a y, you can also write y inverse. Okay, so that would also be allowed. Okay, there's a couple of interesting things that we're going to be thinking about more so tomorrow, but helpful to know for today. If you switch x and y, then you also are switching domain and range. You switch x and y, you are switching domain and range. Now we have kind of briefly seen this because back in chapters 2 and 3, we graphed parabolas that opened up or down. So there's like y equals x squared. And then in chapter 5, in section 3, we graphed parabolas that had a y squared instead. And remember to graph that one, we square rooted both sides and said it was plus or minus the square root of x. Okay, and so we got these parabolas that were opening on their sides. So if you'll remember back to chapters 2 and 3, the domain of this parabola that opens up or down, we said it was always all real numbers. And then wherever its vertex was, it had like a min or a max point. So we could say that its range was y is greater than or equal to 0. Well, down here, this graph is actually the inverse. We're going to look at some like this tomorrow. This is actually the inverse of the parabola. Notice when we did those problems in section 5.3, our domains were restricted because we like started x's at 0. But our ranges were always all real numbers because this arm was going up and this arm was going down. So we've already even seen that domain and range are going to switch. So that's kind of an interesting thing that happens. It can be really helpful when you're studying different functions. The other really good thing to know about inverses is that when you switch x and y in an equation, in a table, or on a graph, if you looked at that thing graphically, it would always be a reflection over the line y equals x. Okay, so every inverse function, or every inverse, is a reflection over the line y equals x of the original function. So the line y equals x, just to kind of review, that's the line where you pass through the origin and you have a slope of 1, so it kind of looks like a 45-degree angle. It goes through quadrants 1 and quadrant 3. That's y equals x. So I'm going to show you an example, one graph example, where we see how it looks like the reflection over the line y equals x. And we'll look at that more tomorrow too. Okay, but those are just a couple of interesting things that occur. So not a lot of your homework problems are like this, but I just want to show you before we get into the equations work. I could provide you with a table of values. The table could be written vertically, or in this case, it's horizontally. So I've got x's on top, and they are -2, -1, 0, 1, and 2. Just like I kind of normally pick those x's. Y's are my second row, and that's -1, 1, 3, 5, 7. I can tell just by looking at that table that that's a linear function because the differences between my x's are constant, and then the difference between my y's are 2. So it has a slope of 2 over 1, or 2. But this table would really be representing my f of x. That's like my original function. So if I want to create a table for f inverse of x, then I just have to swap the x's and y's in the table. So that's like a super easy problem, right? Okay. I'll just name x and y, but I'll just move all the y's up to the top row. So I'll have x's that are -1, 1, 3, 5, and 7. And then I'll move all of the x's to the second row so they become y's. -2, -1, 0, 1, and 2. So that would be like finding an inverse in a table. It's just switching the x and y rows or columns. It's that easy. Suppose I gave you a graph. If I gave you a graph, instead of having all the points labeled for me in the table, I would have to look on the graph and try to find points that I thought were nice points that I could like switch around the x and the y. So just to kind of make sense of this graph, the red line is the function f of x. Okay, so it's labeled f of x down here. The dotted line, this is going to be that line of reflection, y equals x. So once I graph the inverse, we'll see how it's a reflection over that line. But what I would do is I would start looking for a point on the red line that was a nice point. Oh, here's one. Okay. It looks to me like that point, I'm scaling by 2s, it's -2, -6. Right? A point on the graph. And that's an x and a y. So if I want the inverse, I'll just switch those points. And a point on my inverse line should be -6, -2. So that's a point on my inverse. And then to graph a line, I'd really like to have 2 points. So I'm going to be checking, like, is there another nice point for me? You know, it actually looks like this point right here is a nice point on the red line. It looks like it's crossing at 4, 4. Well, if I swap x and y for 4, 4, I'm still at 4, 4. And that should make sense because that point is actually on the line of reflection, so both lines would share that point, right, when we think back to geometry. Okay, so then I have the 4, 4 point on my inverse, and when I draw the line in blue, you can kind of see if you were to fold the paper at the black dotted line, the blue line would map over onto the red line. Okay. So like this part of the blue line down at the bottom will map over here to this red, and then this part of the blue will map over onto the other side. Okay. And they're like equal distance from the line of reflection, a more geometric perspective of it. And like here you might be able over on the sideboard where I have my 2 quadratics, and you might stretch your mind a little here, and we're actually going to see this tomorrow. But like if I reflect that over that line, then it turns into this parabola on its side. Okay, so I could take points like I know 1, 1, I could take 2, 4, okay, and those points of course are on my square root graph. Swapped. So just something to think about. The majority of your homework, however, is not going to be tables and graphs. It's going to be equations. So we'll do a couple, and then we'll talk about how we can verify inverses, and then you should have some time to work on your homework assignment. Okay, so let's say I give you an equation. F of x equals 1/3 x minus 2. Okay, you can tell by looking at this equation that it is linear, right? It's a line, mx plus b. So if you reflect the line over the line y equals x, it's going to be another line. So I know at least my answer should look kind of like a linear function. If I ever get a function that's given to me in function notation f of x, I usually just go ahead right away and change that to y. So I rewrite it, y equals 1/3 x minus 2. And then I start my work for finding an inverse, which the most important thing you got to know about today is switch x and y. So this is going to be x equals 1/3 y minus 2. Notice that I don't move the 1/3 with the x. I'm literally only replacing the letters. Okay, so this technically is the inverse, but we usually like to have our equations equal to y. So now I'm going to move the 2 and the 1/3 to the other side. So just follow reverse order of operations. I would add 2 to both sides first. If you had a fraction times your y, how would you get rid of it? Multiply by a reciprocal. So in this case, we're going to multiply by 3. And then here's the thing that you kind of have to watch out for. If you've already done some addition or subtraction, you move that over, you're really multiplying that whole side by 3. I always like to protect that with a set of parentheses. I'm multiplying the x by 3 and I'm multiplying the 2 by 3. So my inverse function, I could call it y inverse. Right, this is going to be my answer, is 3x plus 6. It would come out to be y equals 3x plus 6, but remember that's the inverse, so I'm just going to name it as the inverse. I just put the -1 on there so that everybody knows. If I didn't want to use that, I could use the f inverse notation too. But it would look the same on the other side, the 3x plus 6. I'm going to move this over. Oh no! Why? I'm just going to keep going and pretend it's not happening. Look, it's still moving. Usually it like freezes on me. We're okay. We're going to be fine. It's just a little blip. Okay, does anybody have any questions about that one? Will you try f of x equals 2x plus 3? See if you can get me the inverse. F of x equals 2x plus 3. What does the inverse function look like? Was y equals 2x plus 3, right?